I am your host, Charles Frye, and I will be telling you today about how to instrument weights and biases with PyTorch. And I'll be working out of a collab today, out of a Jupyter notebook hosted on Google's infrastructure. What that means is that you can follow along if you would like. So what we're going to cover today is how easy it is to instrument weights and biases with PyTorch. So for folks who aren't familiar, weights and biases is a machine learning experiment tracking, dataset versioning, and project collaboration toolkit with a bunch of modular tools. So we're going to focus primarily on experiment tracking today, but as we go forward in this webinar series, we'll also talk about dataset versioning and model optimization with the artifacts and sweeps tools, and collaboration and reproducibility with the reports tool. But today, we will begin at the beginning, the weights and biases dashboard and logging. If you look on the left-hand side of your screen, then you will see a table of contents for this notebook. There's a lot of steps in this that are not related to necessarily instrumenting weights and biases directly. The ones that are actually the parts for instrumenting weights and biases, independent of whatever model it is you're using, are the ones labeled, step 0, 1, 2, and 3, and 4. The rest of them are just sort of something you have to do for every PyTorch model. So we'll also go through that so we can talk a little bit about how to do things in PyTorch in case you're not super familiar with it. And there's going to be a lot of lines of code that are associated or dedicated to those pieces, like defining our data loading, defining our model, all that. That's going to take up a lot of space. But it's going to turn out, if you just look at those steps in particular and look at what you need to do with weights and biases to get this thing going, it's going to be 4 lines of code, 5 lines of code. So we're going to talk about storing hyperparameters and metadata in a config, in a configuration object that gets logged to weights and biases. So you always know with every set of results, what were the hyperparameters and what kind of metadata did I associate with this run. Then tracking our model with W&B.watch, which will automatically log our model gradients and parameters over time so we can watch how those evolve. It's a great way to detect bugs in your training code, or if you're writing your own custom modules or something like that, your gradients might vanish to 0 or, behave strangely, and you can detect that with W&B.watch. W&B.log is the API we're going to use to log everything else, like the loss. We can also use it to log all kinds of custom stuff that we're interested in. We've got another webinar on using W&B.log, just exclusively devoted to how you can use that to log all kinds of different things, from 3D objects all the way down to, your humble scalars. And then lastly, we'll talk about saving your model in a Netron compatible format so it can be viewed on weights and biases. So you can see, with this run that got this results, what was the exact sequence of operations that made up that model. But all this will make it a lot easier to keep track of all your experiments that you're doing. You've got, if you're anything like me, when you're really in the zone on a project, you've got lots and lots of different models doing lots of different things. You may be running a couple in parallel. You got one on one GPU, you got another on another GPU, one's in the cloud, one's on your laptop. If you keep track of that in a Google Doc like I used to, it's very easy to lose track of what was what and what were you thinking and why were you thinking it at that time, and how could I reproduce any particular maybe very promising run or a run that looks like it has a bug in it. So we're going to try and solve that problem with these weights and biases features today. So let's go ahead and do some imports and installs. So we've also got here a couple of lines to set the random seeds and get deterministic behavior out of our GPUs, just to make this collab as reproducible as possible. And one thing you'll notice, the Google Colab does provide a GPU. So with weights biases, we also automatically log system metrics. So you'll be able to see how well you were using that CPU and that GPU during your training, which can be great for profiling or detecting the need to profile your code. So once you've got W&B installed, it's up on pip. So the classic Python package installation library is all you need to install it. That exclamation point here, if you're not familiar with Jupyter Notebooks and Colab, that says, oh, I'm going to do this one in the shell. So open a quick shell up for me and then run this command. So this is what you would do to sort of set up your environment beforehand, before running your Jupyter Notebook with your model in it, or before running your scripts that have models. You would do this pip install command. And I'm making sure I have the latest version of weights and biases with this -- upgrade. We're rapidly adding new features, so it's always a good idea to have this if you're not in an environment where you're worried about individual version changes needing to be closely tracked with a requirements.txt or something like that. So once we got that pip install step done, it's time to import W&B. And because this is a web service where you're logging the information from your runs, then you're going to need to log into that web service first. So this is maybe an uncommon thing to do with a with a Python script or in a Jupyter notebook. But you're going to be logging in so that you can tell our server, hey, it's me. It's Charles. I've got some hot new machine learning runs that I want to tell you about. This is to make sure that it's me, Charles, and not the evil Charles with a goatee trying to log false metrics to my dashboard. So I've already got mine in. You might get a link. It might pop up and say, hey, type in your API key. So if you've never used weights and biases before, you got to go there, you sign up weights and biases, maybe fill out a quick survey about what you're doing with machine learning, and then you can get your API key and put it in. And then it'll get appended to this nice .NET RC file so that you don't have to do that all the time. Once we've done that, now we're ready to actually get into the meat of it. We're ready to define our experiment and our pipeline. So programmatically, I think the first thing that we want to do is define our experiment. What are the hyperparameters? What's the metadata associated with this run? Maybe when you're writing code, you sort of like start by writing the model pipeline, maybe even start by writing the model itself, and then you build the infrastructure around it. But when it comes time to actually run the run, you set your configuration first. Maybe you set that out in the command line. Maybe you set it by writing a YAML file. There are lots of different ways to do it. Some people even make a .py file that gets imported and use the attributes there as their config. There's lots of different ways to do it. We're going to do it with a dictionary here. So we're just going to specify all these things that are going to be useful later for building our model. So we haven't defined how any of these things are going to be used, but that's what we do next. So first we define our overall pipeline. At a very high level, what is it that we're going to do? And the reason why we have to define this is we're doing this in raw PyTorch right now. So if we were using a framework like PyTorch Ignite or PyTorch Lightning or Keras for TensorFlow, a lot of this boilerplate stuff would be already defined and part of their like fit API or .train API. But for us, we've really got to define everything very, pedantically every single step. So let's start by doing that with this model pipeline here. It's going to take in that configuration dictionary of hyperparameters, and then it's going to use that to build our model and data set. That then gets used to train the model. If you look down here at line 13, we take the model, the training data, and all the additional stuff for defining how to train the model, and we run it, and then we test its final performance. So this is a pretty typical model training pipeline here. The only thing that's really different here because of W&B, right? I told you I was going to show you how to instrument W&B. So what's the difference here? We've got this block right here, this with block starting on line 4. This is one way to use W&B. If you check out the Keras tutorial, you'll see another way to do it that doesn't use this with block. But I like the with block here sort of for the same reason that I like using with blocks when I open files. This with block ensures that anything we do to like sort of spin up W&B gets undone, even if your code has an error or runs into an issue. So it's a good idea to use this with block to say, okay, this is the stuff that I'm going to log with W&B. So this is this classic context manager syntax. If you're not familiar with this with block, that's the thing to Google if you want to learn more. So our entire training pipeline here is inside this with block. And then this W&B.init, it's got a couple of, it's got actually quite a few parameters. If you view the source, you can see all those things and what they do. You can also check out our documentation. We've got nice docs for this function because it's so important. So there's lots of, examples, not just the raw parameters, args and returns kind of style. The important thing is you need to pass in a config argument. And this config argument is the dictionary that contains all of that hyperparameter and metadata information. And then that gets added to W&B, and we're going to log that for you to your page for this run online. One important thing about making that work correctly and ensuring that what we have is exactly the same as what gets run in your code is later we're going to use this config here. That's where the hyperparameters are going to come from, right? Rather than using the original dictionary. So the way to do that is this line here, config equals w&b.config. Strictly speaking, this is optional, but I think it's good practice to make sure what gets logged and what gets used are exactly the same. Okay, so this is our overall model pipeline. The only difference from your standard PyTorch pipeline for a computer vision problem like this one is we've got this with block here, this with W&B.init. Oh, one important side note that I have here, we take care to run our code in separate processes, right? You may be worrying, oh man, I just put my entire training pipeline underneath these other people's code, right? And so you might be worrying that we might crash your training run. And so one thing that we do to try and make sure that that never happens is that we actually run all of our stuff in separate processes. So if anything goes wrong for us, like say our servers go down, it's been attacked by a giant sea monster, then that won't crash your code just because you can't talk to us. So in the end, you can sync your code afterwards once the Kraken has returned to the depths from which it came to attack our data center with W&B sync, but your code will always be safe. Let me walk you through what we're going to be doing next. In this training pipeline, there's a couple of key functions, right? There's the function that makes the model data and optimization problem. There's the function that trains the model, and then there's the function that tests the model. So we need to implement all of those things, and most of them are going to stay the same. We've just, as we would in a normal PyTorch pipeline, we've just got a couple of adjustments due to the fact that we're using weights and biases to log stuff. So I'll say that the part where we make the model, the only difference is that we use that config object to pick out all of our hyperparameters. So here we're using config.batchSize right here to build our data loaders. We're using config.kernels to set how many kernels are in our convolutional networks layers. Otherwise, this is all, your classic PyTorch MNIST convnet example. Nothing interesting here, so I'm just going to hop right over both the data loading process and the convnet process. This is going to be different for every project, right? So whatever I tell you here might not apply to what you're doing on your project. And so this is a relatively straightforward and conventional convolutional neural network on the MNIST data set. Of course, building models, building data pipelines, that's actually all the fun of ML research and ML engineering and ops. A lot of it is building these pieces, but that's not our focus here today. Let's move on then in our model pipeline and specify how we train. So this is now, once we've now got to the training logic, now this is where weights and biases really starts to come into play. The two functions are watch and log. So watch is a special function that's especially useful with PyTorch models. It will log the gradients and the parameters of your model every certain number of steps of training. So you can set that number there, how often you want to log the gradients in the models. I tend to use something like, 10, 100, something like that. If it's every epoch, I might log it every epoch. So that's this first line here at the beginning of our train function. I say, hey, we're about to start training this model. W&B, watch that model. This section here then runs training. And down here, I've got this function train batch. That's what really defines the actual training logic. All this stuff around here is just sort of, okay, I'm counting examples and batches. I'm loading the images and labels. I'm using TQDM to give me a nice progress bar. So the two important pieces are train batch and train log. So train batch is the part where we actually do the training. This is standard PyTorch stuff. Put my images and my labels on my device, run a forward pass that gets me the outputs and the loss, run a backwards pass, and then take a step with my optimizer. So improve the performance of my model at the end, and then return the loss for later use. So we've got this train batch function. That's all quite standard. The part that differs is the part where we log what's going on in training. In the code that I wrote before I discovered weights and biases, this would be something like a print statement maybe, or maybe saving something to a file locally would be this train log function. So this is where the difference comes in, this W&B.log call. So what this does is says, hey, W&B, here is the information that I want to associate with this step of training. First, you should give a step number. Okay, what step of training is this? And this should be constantly going up as you're going. So it doesn't have to go up by one every time. So for example, here I'm using the number of images that the neural network has seen as my step. The other thing to provide is this dictionary here, a dictionary that says, oh, okay, here's what happened on this step of training. The epoch was this number and the loss was this. This dictionary here, you can put lots of things in it, much more complicated things than just numbers, using the various W&B media types. Images, audio, video, 3D objects, things like that can also be logged here. But to keep this example simple, I'll just stick with these sort of simple scalar values here. So that's the main difference here. All of this code up here, this is stuff apart from this W&B .watch here. All of this stuff is standard. So really, we've only added this line here and this line here, number 5 in train log. Once the model is done training, we probably want to test it to see, okay, you did well on the training set. How well are you doing on the data you didn't see? That's this testing logic here. The thing that I tend to do at the end here when I'm done with my model is save stuff about my model. So at the very end, once I've got my model done with training, that's when I want to save it. With W&B, the way you save files that you want to associate with a run is with W&B.save. So that's this line 21 down here. One thing you'll notice is that I'm saving the model in this exchangeable ONNX format, the Open Neural Network Exchange format .ONNX here. This format plays nicely with a large ecosystem of open source tools. So we'll see what that looks like once we run training down here at the end. So we've defined the 3 components of our pipeline: make, train, and test. We've built our pipeline and we've instrumented it with W&B. We've added those 4 or 5 lines. So we're ready to run our fully tracked experiment. I'm going to run this cell here, and then we're going to see what comes out. When you start a run with weights and biases, we give you a couple of links to a project page, which is where you can group together a bunch of runs that are all in the same project, and then to a run page, which is a specific page for this particular run that's going to log information about that run here. Let's go and check that out, and let's see what we logged. All right, what this thing is here, you might hear this called the workspace or the dashboard. This is where you can sort of interact with all of your runs, the information that was logged from each run. So what we've got here, because we use W&B.watch, we've got the values for all of our weights, biases, and the values for the gradients over time. So you can see some nice things like the gradients aren't exploding or vanishing. The gradients are decreasing over time. That's a good sign for optimization. This is very useful for debugging. It's presented as a histogram. At any given point on the x-axis, there is a histogram. And then you can highlight an individual histogram to see what that individual histogram looks like in greater detail. You can see a little kernel density estimate on top of it if you prefer a kernel density estimate to a histogram. What else did we log? Well, we logged, this also includes the things that we logged ourselves, the things that we logged by hand with W&B.log. So right here, we've got the loss. It's going down over time. That's good. There's a good amount of noise here because I think this is just the loss on an individual batch. So that can be, that can be quite noisy. It's only 100 or so examples. It's noisy, but it's going down. If you want to get rid of some of the noise in your charts, if you really actually care more about the trend over time, you can use this smoothing operation. So that looks like about the right amount of smoothing to capture the fact that we're really, we're going down here. And you can always include or not include the original in your chart when you're showing that, showing these smooth versions here. And, edits you make to the chart will stick around in this workspace. These are our charts here. There's lots that can be done with these charts, but I want to focus on all the other things that we logged rather than just focusing on these charts. So let's take a look at the system metrics. So this is something that's really great. I used to just sort of like watch top or htop, watch and that's not super reproducible. As you're logging stuff, you will also get these nice system metrics here. So a couple of things that we track the disk IO utilization. This is one thing you really want to pay attention to with your data loaders. You want your disk IO utilization to be super, super high, because that means you're sort of like constantly reading stuff from disk because you're always pushing stuff to your GPU to get trained. So the other metric that we measure, and that's really important for getting the most out of your hardware, is GPU utilization. So this GPU utilization here tells you how hard is that GPU working. And you want to get this as close to 100% as possible. This is, not very well-tuned PyTorch code here. So the GPU utilization is pretty poor. So we could probably fiddle around with things like batch size and the number of workers in the data loader and all kinds of stuff like that to try and increase this utilization number. And thanks to W&B, we'll actually be able to track it and see And you could write things down in your config, your hyperparameters, and your metadata to track your experiments as you try and boost this GPU utilization up to 100%. And as that's going, you'll get to watch your GPU temperatures go up and up and up until you hit the point where you can start cooking stuff on your GPU. We'll also include like a simple representation of your model, the same thing you'd get out of a print statement applied to your model, or model.summary if you were using Keras, with things like the number of parameters and the shapes of the outputs. But actually, there's a way to get a much nicer look at your model than this, and it's in this tab here, this Files tab. We saved that .onnx file with W&B.save, and so that file itself got logged to weights and biases, got synced up to weights and biases. And these ONNX files, we know how to pass them to this Netron visualizer. So this Netron package here can visualize neural networks regardless of what framework they come from, if you put them in that ONNX format. And then you can see just exactly what was the computational graph that was actually used. So there's lots and lots of stuff here. You can get these things out as PNGs and SVGs. So when you need to come back later, rather than reading your PyTorch code, maybe you come back and look at one of these ONNX files to see what your model looked like. They also make for great figures in blog posts, maybe even papers. The other thing that I jumped over as we were going down here was we also capture everything that goes out to that standard out. So I printed out a representation of the model there and also the loss. This information here is logged automatically to our servers. So, that standard out is pretty ephemeral, right? If you were to close that terminal or lose access to it somehow, you would not have all that information. And there's a lot of stuff that gets logged, maybe errors from certain libraries or warnings that you might not necessarily want to sit around watching to see if they pop up. So we'll save that for you and put it online so that you can find that stuff. And it's also useful, like maybe you don't notice the bug until later and you're like, wait a second, when did I start getting this random warning message from PyTorch or from TensorFlow? And you can go back and look at the old logs of your previous experiments and try and find the exact point at which that message started to appear. So it's easier to find and track down those sorts of bugs. I guess I'll just also say there's this nice summary page here at the top, this information about the run that gives you things like useful stuff for reproducibility, where it was run, versions of different things, the command used to run them, all kinds of stuff like that. And also, summarizes that config and anything that you describe as a summary. You can learn more about how to write summaries by clicking that link. So lastly, what makes this run special? This run is from the PyTorch demo webinar. So you can write little notes to yourself. This is a nice place to give yourself tiny little notes from your experiments, or you can write longer things. If you really want to write a lot about an experiment, I would recommend you use our report function. So we've got some YouTube videos about how to use reports. We'll also be doing demos about those in this series. So I look forward to seeing all of you at those demos to learn more about these weights and biases features. And we'll have a wonderful, wonderful time. Looking forward to it. Take care. Hey friends, Charles here. Thanks for watching my video. If you enjoyed it, give it a like. If you want more weights and biases tutorial and demo content, subscribe to our channel. And if you got any questions, comments, ideas for future videos, leave a comment below. We'd love to hear from you.